All right, hello chemistry friends. So today's class is going to be a little bit different. We're going to be going through the same exact lesson that we would have been if we were doing a live Zoom call, but instead of doing a Pear Deck assignment, anytime where you would be typing in Pear Deck, you're just going to answer the questions here directly on the Edpuzzle. Okay, just as our normal classes, these are just thinking questions, they're practice, so they're not going to be graded necessarily, but please do make sure that you complete the entire lesson because number one, this is the only time I'll officially be teaching this content, and number two, I'll mark your attendance for today based on you completing the Edpuzzle today, okay? So we're going to get started with the warm-up. So here in a second, you're going to get a question to pop up where you're going to define the word temperature. Reminder, your answer should not contain the word heat. Okay. Hopefully you correctly define the word temperature using our official chemistry definition, which is that temperature is the measure of average kinetic energy. It is not energy itself. It is not heat energy. We'll learn about that next week, I promise. But it is rather the measure of average kinetic energy. In other words, how fast or how slow particles are moving. Yesterday, you learned about the 3 units of temperature that we use in the world. We have Fahrenheit, Celsius, and Kelvin, and hopefully you got an introduction as to why we're going to be using Kelvin mostly throughout this unit. Okay, so the next slide, our next warm-up question is going to be multiple choice questions. There are going to be 3 of them. So on the screen, I have 3 particle diagrams, and you're going to see 3 questions pop up here in a moment. Okay, question number 1. Which particle diagram, A, B, or C, represents particles in the liquid phase of matter? Question number 2. Which particle diagram, A, B, or C, represents the phase of matter in which the particles are arranged in a rigid crystalline structure? And question number 3, which particle diagram, A, B, or C, has particles in the phase of matter, the only phase of matter, where particles can be compressed or expanded due to changes in pressure? All right, so hopefully you got all of those. I think Edpuzzle tells you the correct answers, but if not, here they are. Question number 1, which phase of matter exists as, which particle diagram is showing a liquid? We have letter B is showing the liquid in which the particles are close to each other. Okay, they're basically touching here, but there's no pattern to them. They're completely spread out along the bottom of the container, but they're still close to each other. Okay. Question number 2, which particle diagram shows the phase of matter in which particles are arranged in a rigid crystalline structure? Crystalline structure, the root of the word is crystal, should help you remember that we're talking about solids because crystals are solids. And so as you can see here, this solid diagram, we know it is such because the particles are as close to each other as they can be and arranged in some sort of pattern. Here they're in straight lines up and down and straight lines going across. Okay, and then question number 3, we hadn't talked about specifically. Tim and Moby mentioned it. I believe I may have mentioned it, but this is the reason why the whole second half of our unit is going to be focused on gas particles, because the question was which particle diagram has particles that can be compressed or expanded, and the only phase of matter that this will happen when we change the pressure will be gas particles. As you can see here, the gas particles are very spread out. They're totally randomly placed in this container, and so because of that, if we increase the pressure, we can squeeze them a little bit closer together like an air compressor, or if we remove the pressure, they can also spread out because that's what they want to do. They want to spread out as much as they can. Okay, so hopefully you have a good understanding. Take a quick screenshot or something of the 3 phases of matter because you're going to keep drawing them, and we're going to actually draw them in a little bit different way starting in our next class, because what we're going to be focusing on from now on is not the individual phases of matter, but more so when they change. Okay, and so at the end of class, you're going to be able to say this statement: I can identify the phase of matter of any element at a given temperature. Okay, and to start to do that, we're going to start thinking about what phase changes are, and these letters will make sense here in a moment: melting point and boiling point. Okay, So we're going to do a little bit of a thinking question. You've probably answered this one before last week in our asynchronous work, but because we're focused in on phase changes, the question is, how do phase changes happen? So I want you to imagine you have a cup of ice. Okay, I did have some earlier, but it turned into the liquid and I forgot to put it in my freezer. But imagine you have a cup of ice and we want to turn it into a liquid. What has to happen in order for that to take place? I want you to try and answer using the words temperature, particle movement, and kinetic energy in your answer. All right, so hopefully you noticed the trick between these three criteria: temperature, particle movement, and kinetic energy. They're all basically the same thing. In order to go from a solid ice cube to liquid water, we want to melt it. And how do we melt it? We typically add heat energy. Okay, we put it in the microwave, we leave it out in the hot room, we put it in the windowsill, or we put it on the stove. That's how we can melt water to get it from its solid state to its liquid state. And those are going to be the phase changes we are looking at. Okay, we're also going to be looking at how to go from a liquid to a gas, which also requires adding heat energy. And then going backwards, we're going to look at a little bit is exactly the opposite. Okay, so boring notes time, but go ahead and screenshot these. You don't have to copy them down because I think they will make sense as we go through our lab later on this week. Okay, so I'm just going to quickly read through this. Remember, temperature does not measure heat. They are, of course, related. Instead, temperature provides scientists with a measurement of how quickly particles are moving and how much kinetic energy they are using. When the temperature is low, particles will be moving very, very slowly, and in their slowest state, they will cause them to be in the solid form. As temperature increases, due to heat being added, particles will begin to move faster and faster and faster until they reach a specific point in which you can push them into the liquid state. And if you give them enough energy, they can eventually become gases. Okay, and so just to give you kind of a visual of that, in order to go from a solid to a liquid, particles here are moving very slowly. We need them to move faster, and so we're going to add energy to the system. If we wanted to go backwards and freeze this liquid and turn it back into a solid, the particles have to slow down, which means they're going to remove energy or release energy from the system. Okay, these are going to be the ones we focus on first, but then we're also going to look about how to go from a liquid to a gas, and same thing, because we're going to particles that have higher amounts of energy, you have to add energy to the system. If we want to take gas and turn it back into a liquid, particles have to slow down by releasing energy from the overall system. Okay, some questions I got yesterday: is it possible to go from a solid all the way to a gas? Is it possible to go from a gas all the way to a solid? The answer is yes. We'll be talking about those next week, but for right now, we're just going to be talking about taking one step at a time. Okay, and so the question is, how do we know we've reached the point when a solid has enough energy to become a liquid? How do we know we've reached the point when a liquid particle has enough energy to turn into a gas? And that's going to be our new vocab today. Here's temperature again, but the point at which we know that we have enough energy to go from a solid to a liquid is called the melting point. Officially defined as the temperature when particles have enough energy to change form from solid to liquid. Okay, another word for melting point is freezing point, because in this case, going from a solid to a liquid, you add energy to the system, and at that specific temperature, they can go up a phase of matter. But if you remove energy from the system, the temperature at which they change from a liquid to a solid is exactly the same. You'll see that here in a moment on our next slides. Okay, and then similarly, boiling point, temperature when particles have enough energy to change from liquid to gas. This is going to be equivalent to what is known as the substance's condensing point, when they have released enough energy to go from a gas down to a liquid. Okay, so what are we going to do with this? Well, on this screen, you're actually going to see three letters show up here in a moment. Okay, the question is, what phase of matter will you see at different temperatures in relation to a substance's melting point and boiling point? So over here on the left-hand side, you see a temperature arrow, meaning we're starting from low to high. And I've marked where the freezing point of a substance is and where the boiling point of a substance is. So what you're going to do is in a moment you're going to have an open question, and it's going to ask you to label A, B, and C. What phase of matter are we going to see at these relative temperatures compared to a substance's freezing point / melting point and boiling point / condensing point? So hopefully you got that. If not, don't worry. I'm going to go through an example, and this time I'm going to actually go through an example with our dear friend water. Okay, and we're actually going to assume that we know some things about water, including water's melting point and boiling point. Okay, if you Google this information, it's probably going to come up in Fahrenheit, but I'm also going to include Celsius because Celsius is the unit that scientists use, and we'll use Kelvin later on this week. But if you look up the melting point or freezing point of water, you will see that it is equivalent to 32 degrees Fahrenheit, which is about how cold it is today, which is not very pleasant. And that is equivalent to 0 degrees Celsius. Okay? And so let's pretend that the question says, I have water at room temperature. And let's just say room temperature today is about 70 degrees Celsius. Well, if I'm at 70 degrees Celsius, I know that I am at a temperature higher than 32 degrees, sorry, 70, oh my goodness. Room temperature is not 70 degrees Celsius, my friends. It is 70 degrees Fahrenheit. 70 degrees Celsius would be way too hot. We'd all be burning up. We'd be dead. It wouldn't work out, okay? But 70 degrees Fahrenheit, which is close to like 20 degrees Celsius, is higher than 32 Fahrenheit. And so that means we are at a temperature past our melting point, meaning we are not going to be a solid, because we will only be a solid at temperatures that are less than the freezing point / melting point, okay? But we don't quite know if our water is going to be liquid or gas, because we also need to compare it to the boiling point of water, which if you look that up, the boiling point of water, most people are actually more familiar with it in Celsius because it's a nice pretty number, 100 degrees Celsius. And Fahrenheit, does anybody know? The boiling point of Fahrenheit is 212 degrees Fahrenheit, which is when water is going to start to boil on your stove, okay? And so what you're going to do is you're going to be like, okay, we're at 70 degrees Fahrenheit. We know it's greater than 32, but now we also know that it is less than 212, meaning we have a substance that has melted, but we don't have one that has yet boiled. And so that tells us, that water is going to be a liquid at this specific temperature, okay, at 70 degrees Fahrenheit, because it is in between these two temperature values. Okay, if we are at a temperature greater than 212 Fahrenheit or greater than 100 degrees Celsius, we would have a gas. Okay, but that is not the case for water at room temperature, and that's why if I had a cup of water here, it would be in the liquid state. All right, so last thing that we're going to do is we're going to take this idea of comparing relative melting points and boiling points and use it with things other than water. Okay, we're going to talk a lot about water in this unit, but there's other things that can change from solid, liquid to gas. In fact, every element on the periodic table can be a solid, a liquid, or a gas. Okay, and so what you need to know is the melting point and the boiling point of all of those elements. And luckily for you, on Table S, the back of your periodic table on your reference table has that information. You have the list of selected elements, which is the vast majority of them, and if you look right over here, you have the melting point and boiling point for each element. Okay, and so what you can do is you can look at a question and say, what phase of matter will hydrogen be at 273 Kelvin, which is a very important temperature. It's standard temperature. Okay, and so you can look and say, okay, hydrogen melts at 14 Kelvin and it boils at 20 Kelvin. You can ignore that decimal. It's there for significant digit reasons, but we don't need to worry about it. It's just 20. And so the question was about 273. Well, 273 is definitely bigger than 14, and it's also definitely bigger than 20, meaning we have passed our boiling point, So hydrogen will have boiled, making it a gas at that temperature 273. Okay, so what you're going to do is you're going to go ahead and practice that information for iron, oxygen, and mercury. If you do not have the reference table, look on Google Classroom. It was posted with today's assignment. Make sure you are looking up the melting point and boiling points in Kelvin if you are using Google, and you're going to compare them to the temperature in the question, which is 273 Kelvin. Okay? So I'm going to walk you through the first one before you move on to the next two, just to see where you're at. And we're going to look up the melting point of iron, which if we look on table S of our periodic table, let me go ahead and open that. All right, so I have my table S open, and I'm going to look for iron, which is number 26. And if I look at the melting point is 1,811. So I'm going to write 18, oh my goodness, 1811 Kelvin. And you should be able to answer the question from that point, but just in case, the boiling point is 3,134. So I'm going to write 3,134 Kelvin. And the temperature that we're talking about, meaning the environmental temperature, is 273 Kelvin. 273 is less than both of these numbers, so that means that we are lower than our boiling point. Lower than our melting point, which means we haven't melted yet. And so iron is going to be a solid at this temperature. Okay, which honestly, most of you were probably already familiar with because you know a little something about iron. You probably already know the answer for oxygen, so you're going to prove it to yourself on the next slides. And then mercury, some of you may or may not know, but you're going to try it on your next slides. Okay? So just to come back and check with you, my friends, oxygen is in fact a gas at room temperature. That is because if we look at the boiling point of oxygen, it is only 90 Kelvin, meaning at the temperature 273, you will have boiled, making it a gas. And if we look at mercury, mercury is a special element. It is only one of two elements that is naturally a liquid at room temperature because the melting point is 234. So 273 is higher than that number, but it is less than the boiling point. It's 630, meaning we have melted, but we have not yet boiled, meaning that our last substance, mercury, is going to be a liquid at 273 Kelvin. All right, my friends, so we will be doing a lab on Thursday where we're going to be seeing what is actually happening at melting points and boiling points. We're going to be looking at water, of course, and you're going to watch me melt and boil water for like 30 minutes straight. It's going to be great, but we're going to see something pretty interesting happen, okay? So hopefully you learned a lot today. Please make sure you click submit on Google Classroom. That will be your attendance for today, and I will see you all on Thursday. Okay, goodbye, my friends.